So let's move on to what we should be up to now. Now we are up to testing hypotheses for a variance. Now I did the confidence interval. We can also do hypothesis tests. And here is one or two slides which are copies of hypothesis test slides that you've seen previously. This slide has been there several times. How do we do hypothesis tests? Well, we formulate the hypothesis. We choose or have been given the alpha level. We calculate some statistic that measures the data in relation to the hypothesis. We either find the critical value and make the judgment, or we find the p-value and make the judgment. And then, as I said, we make a conclusion based on either p-value or critical value. Here is how it looks in formulas for the variance situation. Again, it's almost the same slide as you've seen regarding mu previously. We can test the null hypothesis regarding the variance, and we can have an alternative that may be two-sided or it may be one-sided. Both situations could occur. For variances, most often one-sided, because variances typically, at least from production point of view, variances should be small. And then it's a one-sided thing. But I mean, there could be other situations where it could be two-sided. I cannot come up with one, but I'm sure it could be there. How do we do it, theoretically? And, sorry for jumping. Here it is, the test statistic. It looks a lot like what we saw a minute ago, before the break, that what we do is basically to take the computed variance, that is the data, and directly compare it with the hypothesis, with the null hypothesis. We simply see how much larger is the variance than the null, than the claimed, than the hypothesized variance, and to make it something that we can measure sort of from probability theoretical point, we multiply it by n-1 because the theory tells us that this is the one behaving like a chi-square. So it's just a technical scaling such that we know how it behaves. Then we can measure whether a computed variance is much too unlikely larger than the claimed variance or not. And we use the same chi-square distribution, which I just used for the confidence interval. We use that for the hypothesis test also. And then we have this beautiful table, which is almost a copy of similar tables that you've seen previously. That is those... it's really a terrible table, but I mean, I've gotten used to them now after 28 years. So you can maybe get used to them also if you want. It's basically just giving sort of the decisions to be made depending on which situation we're in and depending on what the data is telling you, right? So we have situation 1, situation 2, situation 3. We can only be in one situation in a given situation, so we have to choose. Are we in one or the other or the third situation? If we are in a situation where we are trying to prove a variance to be too large, to be larger than the claimed variance, then we reject if this is again the observed, you could say this is the observed chi-square is larger than the critical chi-square coming from the distribution. In the one-tailed case, we use the thing where we have alpha here. So this is chi-square alpha. In the two-tailed thing, if we are in the two-tailed situation, such that we will reject the null where if the variance is either too small or too large. Yeah, that's what it says here. If the variance is too small, I reject, or if the variances are too large. And when I say that, I mean the variances as it comes out of this observed test statistic. If it becomes too large or too small, I reject. And this is, I hope you slowly get used to this way of talking and this way of thinking, because this is something that we do again and again. We've done it a number of times, and we'll do it even more times in this course. Just in different situations for different concepts. But we do this hypothesis testing confidence interval again and again. So that's the theory of it. So we jump to the